Hey all, welcome back. Professor Marinos again. And things are really heating up in these thermodynamics lectures. In the last lecture, we described how you can determine whether or not a reaction is going to occur spontaneously when the system is in its standard state. And now we're going to move to describing whether or not reactions will be spontaneous or not in their non-standard states. How can you calculate the delta G of a reaction when you don't have just tabular values to look up? And then we're going to derive what the actual equilibrium state is for any given system, given a set of starting conditions of that system. So let's launch right into it. So for this video, our learning objectives are first, that by the end of this video, you'll be able to determine the Gibbs free energy of any system at constant pressure, not just a system that's in its standard state. And secondly, that you'll be able to determine the equilibrium condition of any system at a constant pressure for any given chemical reaction that can occur within that system. So I just want to start off this lecture with a quick definition of a term that we're going to use a lot, because who doesn't love starting off a lecture with a random definition? And that term is activity, denoted by the Greek letter alpha. And activity of a chemical in a system is simply the effective concentration of that chemical divided by the concentration at standard state. So you'll notice I put the word effective in here. What exactly does that mean? Well, I want you to just pretend that I actually didn't put that in here for now, because for most cases, you can assume that the concentration of a chemical in a system divided by its standard concentration does indeed equal its activity. There are certain exceptions to this rule, which is why I put this effective bit in here, but we're going to touch on those later. But just to get these general concepts to begin with, I just want you to treat this as a concentration in the system divided by the standard concentration. So what is this for a gas? Well, the standard state for a gas is a gas considered at 1 bar pressure. And so if you express the pressure of a gas in your system in terms of bars, then the activity simply equals that pressure in bars. So you have the partial pressure in bars divided by 1 bar equals your activity. Similarly, for a solute in a dilute solution, you'll recall that the standard state for a solution is a 1 molar solution, so 1 mole per kilogram. Alpha is simply the molar concentration of your solute. So if you have moles per kilogram on the top and 1 mole per kilogram on the bottom, then those units just cancel, and you end up with alpha equaling your molar concentration. And for any pure solid or pure liquid, the activity is always 1. So let's move forward with these definitions and see what we can do with this concept of activity.
So just to review again, for any process acting on a system, the change in free energy resulting from that process, delta G, is equal to the change in enthalpy minus the temperature multiplied by the change in entropy. And this is true for any process that's occurring at a constant pressure and temperature. But this can also be rewritten to express the Gibbs free energy that's contained within a system state, simply just by removing these deltas. And so at any given point in time, a system's Gibbs free energy can be obtained by simply stating G equals H minus Ts. The Gibbs free energy equals the enthalpy of the system at any time minus the temperature multiplied by the entropy. Now, using this, we can restate the formula for the change in Gibbs free energy in a chemical reaction. We can state it as the Gibbs free energy of reaction, delta G sub R, is simply equal to the Gibbs free energy of the products summed minus the Gibbs free energy of the reactants summed. And you'll also recall that another expression for the Gibbs free energy of a reaction is simply delta G sub R equals delta H minus T delta S. And if you put little degree signs over these, then that indicates you're measuring something at a standard state, which we've discussed before. That means temperature equals standard temperature, 298.15 Kelvin. The concentrations equal standard concentrations, so that's unit activity, 1 molar or 1 bar pressure, depending on if it's gaseous or aqueous, and a standard pressure. And the nice thing about this standard Gibbs free energy is that it's calculable from tables. They've calculated the standard enthalpy and standard entropy of many, many chemicals. So you can know a priori, if your system is in the standard state, what the Gibbs free energy of a reaction is going to be. Now, this formula above doesn't have the condition on it that things need to be in the standard state, but it's not as easy to ascertain what delta G is going to be. This is measurable via a calorimeter, of course, but what if you don't have your pocket calorimeter with you? What do you do to calculate the delta G of a reaction at non-standard state? Well, there are a few tricks that we need to do to get to that point, but let's explore those a bit more in depth. And so let's come over here and consider this equation again. If a system has a free energy G, the free energy in that system is just the sum of the free energies of all the components that make it up. So consider a chemical B that exists in that system. The free energy of the chemical B will just be the enthalpy contribution of the chemical B minus the temperature times the entropy contribution of chemical B. And so we can define this at a standard state condition by putting a 0 on it. And now what I want to do is I want to ask you to trust me on something. And the reason I want to ask you to trust me on something is that the formula that I'm going to give you next is something that would take a long while to derive and kind of derail us. So I just want to have you take it on faith that this equation is correct. So we've defined the standard free energy of a component in a system, of a chemical B. But what if that chemical is not at its standard state? What is the free energy contribution of one chemical in a system to the total free energy that exists in that system? That can be given by the following formula. The free energy contribution of B to the total system is equal to the free energy contribution of B at standard condition plus R, the ideal gas constant, times the temperature of the system, times the natural logarithm of its activity, the activity of B. And again, you're going to just have to trust me on that one. And so, put that formula in your pocket. This here, GB at standard condition, is called the unit chemical potential of the chemical. And G sub B is simply just called the chemical potential at any state, not just at a standard state, but assuming constant temperature and pressure, as all these equations assume. So, now what can we do with this concept of chemical potential? Well, you'll notice that we can now plug these chemical potentials into this formula that we have up here, where the delta G of reaction is equal to the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So let's kind of go along this track and push this a little bit further. Okay, so now let's consider the most simple chemical reaction you can imagine. A yields B reversibly. Now, we said that the Gibbs free energy of reaction for this reaction, delta G sub R, is equal to the standard Gibbs free energy of the product B plus the ideal gas constant times the temperature of the system times the log activity of B. So that's the free energy of the products minus free energy of the reactants. standard Gibbs free energy of A plus, again, the ideal gas constant times temperature times the log activity of A. Okay, so now take these standard free energy terms. We have the standard free energy of B minus the standard free energy of A. And that is simply the standard free energy of reaction. So that is a known value. That's a value that's been measured by scientists and put in tables for your use. So already we've kind of simplified the problem by giving us recourse to already known values. Okay, but what about all these RT log activity terms? What can we do with those? Well, we have the RT log activity of B minus the RT log activity of A. And you'll recall that through the properties of logarithms, subtracting two logarithms is the same as dividing the thing inside the logarithm. So this can just be restated as RT times the log of the activity of B over the activity of A. So now we have the standard Gibbs free energy of the reaction plus RT log and this thing that's being divided here, and that equals the Gibbs free energy of the reaction. And so you can see the Gibbs free energy of the reaction at any concentration at any temperature for the system is calculable. Simply by looking up the standard free energy or calculating the standard free energy, feel free to calculate it, and then using this kind of fudge factor term that's after this, the RT, ln, and whatever this quotient is. And so this, instead of just having to do reactions at standard states and predict whether a reaction at standard state is spontaneous or not, you can now pick your own temperature to do a reaction at, and you can pick your own concentrations to do a reaction at. So this is really nice, because now you can compute for any arbitrary starting concentration and an arbitrary temperature whether or not a reaction is going to be spontaneous in a system. You're no longer limited to standard state conditions. So this is a very powerful tool in your toolkit. Now let's consider a more complicated reaction. Let's say, so previously we had A yields B. Let's spice things up by saying now 2A yields B plus C. Let's calculate the standard, or let's calculate the non-standard free energy of reaction for this equation. So again, delta G sub R equals the standard free energies of the products, B plus C, minus the standard free energies of the reactants. But you have to multiply it by 2 here, because there's 2 amounts of reactant removed for every amount of product produced. And again, this just equals the standard free energy of reaction for this chemical formula, this chemical equation. Now, let's go on to the RT log activity terms. We have the RT log activities of the products, B and C, added together, summed together. Minus 2 times the RT log activity terms of the reactant A. And so again, using the properties of logarithms, adding logarithms multiplies the things inside the logarithms, subtracting logarithms divides the things inside the logarithms. We can rearrange this to then just be the ideal gas constant times temperature, RT, times the natural log of the activity of B, times the activity of C, divided by the activity of A squared. And so you'll notice that this RT log term keeps ending up with something inside the log term that is related to the stoichiometry and the products and reactants in the reaction. And we call this Q, the reaction quotient. So this reaction quotient Q is actually really easy to figure out for any reaction that you can imagine. And it's equal to simply the product as represented by the big pi sign. So that's multiplying everything to the right, just like sigma is summing everything to the right. Of the activities of all the products, sorry for using the word product twice, very confusing, I realize, raised to n the stoichiometric coefficients of all those products, divided by the same of the reactants, the products of the activities of all the reactants raised to their stoichiometric coefficients. So let's just take a really wacky example and write the reaction quotient for it. Let's say we have an equation, say 7w plus 3x yields 18y plus 1/2 z. Sure, why not? The reaction quotient for this chemical equation will just be written as the activity of y raised to the 18th, since the coefficient of y is 18, times the activity of z raised to the 1/2, over the activity of w raised to the 7th, times the activity of x raised to the 3rd. Okay, so we can use this quotient in our Gibbs free energy formulas to then determine whether or not a reaction is going to be spontaneous at any concentration or any activity of the reactants and products in a chemical reaction. So now, for any system with arbitrary starting concentrations of reactants and products and at an arbitrary temperature, we now have the tools to determine whether or not the relevant reactions in that system are spontaneous or not. And we can also use this exact same tool to determine where the equilibrium point is of that system. We recall that at equilibrium, the standard free or the free energy of reaction equals 0. So we can rewrite our equation again. The free energy of reaction equals the standard free energy of reaction times the ideal gas constant times the temperature of the system times the log of the reaction quotient. And so we can just plug in 0 into the left-hand side of this equation and rewrite it again. 0 equals the standard free energy of reaction plus RT ln Q. And the temperature of the system is fixed, the gas constant obviously is fixed, and the standard free energy of reaction is fixed. So the only unknown in this equation is Q. So let's solve for Q. We can just do some easy algebraic rearrangement of this. Exponentiate both sides. And we're left with Q at equilibrium, the reaction quotient at equilibrium, should equal E raised to the standard free energy of reaction divided by the gas constant times the temperature. So this is the equilibrium reaction quotient. And this is just simply a rearrangement, again, of the equation for the free energy of reaction when that is set to 0. Now, we also call this equilibrium reaction quotient K. So you'll see K values published for tons of different reactions. And this is called the equilibrium constant. And so this is just the quotient Q at equilibrium. And so this is obviously defined for a set temperature because this equation on the left-hand side here has a temperature dependency. So if you ever look up K values in a table, they'll always be defined for a certain temperature. And if your reaction happens at a different temperature, you'll have to rejigger it to figure out what the K at your desired temperature is. Now, just one final note. We've talked about the gas constant a lot, and I just want to tell you what this is. Well, actually, I won't tell you what it is, but I'll just give you the number for it, just in case you don't remember it. It's 8.3145 joules per mole per Kelvin. Now, you notice that the top has joules, and so if your Gibbs free energy, standard Gibbs free energy is in joules, you're good. because those values will cancel in the exponent. But if they're not, if they're in kilojoules, for example, you need to divide this number by 1,000 to get your equations to work correctly. So just be aware of that. Just make sure that your units match when you're using the gas constant. Let's work a simple example problem to see how these principles can be applied. An aqueous system at 300 Kelvin contains chemical A at an initial concentration of 3 molar. Chemical A can undergo the following reaction. A yields B reversibly with a standard Gibbs free energy of negative 1.729 kilojoules per mole. What are the equilibrium concentrations of A and B? So as this reaction progresses, what is the final state of this system? Okay, let's get to it. Let's begin first by calculating K, the equilibrium constant, or in other words, the reaction quotient that must obtain when the system's at equilibrium. And again, that's E, the number E, raised to the negative standard free energy of reaction over the gas constant times temperature. So let's just plug in the numbers that we know already. That's E raised to 1.729 kilojoules per mole. So recall this is in kilojoules per mole. So we need to use the gas constant that's expressed in kilojoules per mole, which is 0.0083145, times the temperature of the system, which was specified as 300. And you can plug this into your calculator, and that comes out to be 2. Oh, how awesome is that? A whole number for your K. That doesn't happen very rarely. I think you will intuit that I kind of jiggered this to get that number. But I'm allowed to do that. This is a made-up reaction. Okay, so again, let's consider our reaction and what the reaction quotient must equal. Our reaction is A yields B reversibly. And let's set up what our initial reaction quotient is. Our initial reaction quotient, which we'll denote as QI, is the products B on the top. We have 0 moles of products B at the beginning of the reaction, and we have 3 moles of reactant A at the beginning of the reaction. So our initial reaction quotient is 0 over 3. Now, let's say as the reaction progresses, there is X amount of B produced by the reaction. So as this reaction progresses, how is our reaction quotient going to change? Well, so now we can use this quantity X to determine what the reaction quotient will be as the reaction progresses based on our initial conditions. If X amount of B is produced in the reaction, then as the reaction progresses, the concentration of B will be 0 plus X, because we started with 0. And the concentration of A will be 3 minus X, because we started with 3 moles of A, and for every mole of B produced, we lose 1 mole of A. And so now, the reaction quotient at equilibrium, again, will equal K, which we calculated to be 2. And we can just set this equal to the algebraic expression that we have for the reaction quotient in terms of the amounts of B produced, which is X over 3 minus X. And this is a pretty easy equation to solve. So let's just solve for X, and that should give us the amount of B that exists in the system at equilibrium. Some algebraic reshuffling gives you X equals 2. That's nice. So now use this X equals 2, plug this back into your expression for the reaction quotient using X, and you get the activities of both A and B. So the activity of B and the activity of A should equal X and 3 minus X respectively. So just plug X equals 2 into the reaction quotient, and you end up with 2 for the activity of A and 1 for the activity of B. And these are approximately equal to the concentrations of B and A. You'll recall that effective concentration and actual concentration aren't always exactly the same, but for most systems, they're darn close enough.
So you've now solved for the equilibrium concentrations of the system. At equilibrium, there is a concentration of 2 molar of B and 1 molar of A. Awesome. So there's been a lot of math flying around in this lesson, and so I just want to summarize the take-home equations that you're going to be using over and over again in this class. And you'll need to put these in your pocket and keep them handy because we are going to really, really work them hard. The first is the equation for the Gibbs free energy of reaction, denoted delta G sub R. And this is simply the standard free energy of reaction for a given reaction plus the ideal gas constant times the temperature times the natural log of the reaction quotient. And you recall that the standard Gibbs free energy of reaction can be calculated from standard enthalpies and standard entropies, or in lots of cases it will just be given to you, or you can look it up in a table for a reaction of interest. Now, to determine the equilibrium condition of a system, we can set the left-hand side of this equation equal to 0, because at equilibrium the Gibbs free energy of reaction equals 0 in a system. And then we can rearrange everything to solve for Q. And rearranging this gives us the equilibrium constant, or K, for a given reaction. And K is equal to E, the number E, raised to the power of the negative standard Gibbs free energy of reaction divided by the gas constant times temperature. Finally, to express Q in any given reaction, the reaction quotient, you simply multiply all the activities of the products together raised to their stoichiometric coefficients, and then divide that by multiplying all of the activities of the reactants together raised to their stoichiometric coefficients. So for any given chemical reaction that you've described in a equation, you can determine the reaction quotient for this equation, as we've seen in a few examples. So now you have all the tools in your tool belt to be able to not only determine if a reaction is going to be spontaneous for any reaction at a set temperature and pressure, but you also have the tools in your tool belt to determine what the equilibrium concentrations of reactants and products are going to be given an initial condition in a system and given the possible reactions that can occur in that system. So that is all I have for you. We're going to work a lot of these problems in class. These equilibrium problems can get a lot more complicated, so we're going to work on shuffling around a lot of these variables and arriving at equilibrium concentrations and doing free energy calculations and such. And this just takes a lot of practice. And then in the next few weeks, we're going to move on to a lot of environmental applications for these equilibrium equations. The whole world is governed by equilibria. So can't wait to see you there. We're going to really understand how the world works as dictated by thermodynamics. Thanks for listening.